S. Chan presents educational video lectures. Difficult concepts made easy. Study anywhere, anytime.
Welcome to S. Chand Academy, and I am Anmol Bhatia. The course that we are doing is Applied Thermodynamics, and the topic that we will be doing will be work and energy.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box.
So, there are certain basic definitions which would be helpful in solving the perspective numericals. Number one is energy. So, energy is basically the capacity for producing a particular effect. Let's say that effect is lifting of load or running that particular engine. That is particularly related to producing that particular effect. So we have different types of energies. One is work, another is heat. Then we have certain energies like potential energy, internal energy, or the magnetic energy. So for the purpose of thermodynamics, we will consider only these energies which are listed here. Now there are certain definitions. Let's say the first one is work. So work is that particular energy which is there in transition, and the sole effect of that particular work is related to raising of that particular load. So work is basically done to raise that particular weight, and that work is there in transition. Heat is basically the energy that transfers due to the temperature differences or temperature deviations. Then you have the category of internal energy. So energy which is associated with random motion of the molecules and how those molecules interact. That internal energy is particularly that particular condition. Then you have enthalpy. Enthalpy is U plus PV. It's having a general definition. And W and Q, which is work and that particular heat, they are basically energy in transition, and their transference takes through the rough boundaries, and they are particularly called as the path functions. And the other sort of energies like internal energy, enthalpy, potential energy, kinetic energies, they are basically the energies which are there for the system, and those energies are basically contained in that particular system. Now let's say, for an example, you have a battery, and that battery is connected to that particular resistor, and this system you are considering, and there is a boundary being used to denote that particular system. Now this resistor is being replaced with the help of an arrangement whose sole effect is the raising of that particular load. So the motor is connected, and that motor is required to raise that particular load. So the flow of current from battery as work, we will consider that electric energy is being converted into that work. So work is said to be done by the system on the surrounding if the sole effect external to the system could be the raising of the load. So the sole effect here is to raise that particular load. So the work is done by the system on the surrounding. So the figure indicates that particular condition. Now we have to make sure that we use certain sign conventions in order to indicate U, W, H and Q. So work done, when it is done by the system, it is considered to be positive, and when this work done is done on the system, it is considered to be negative one. So two conditions: one is work done to be positive, which is work done by the system, and negative when it is considered to be done on the system. And reverse for the Q is true, like heat added to the system is considered to be positive, and when the heat is removed from the system, we consider it to be negative. Now, if there is change in internal energy or enthalpy, if this change is positive, then this U and H are considered to be increased. The values of those are considered to be increased, and if this change is negative, then the value is said to be decreased. And as I have told you that this W and Q are those energies which are there in transition, and the transference basically occurs from those particular boundaries, and they are basically the path functions. And other set like internal energy, potential energy, they are considered energies of the system, and they are considered within the particular system. Now we will be looking at certain mathematical relationships for the particular cases, like we will be considering it for the quasi-static process. Quasi-static process I have already explained in my previous videos. If you haven't watched those videos, you can visit the playlist of S. Chand Academy channel. So considering the PV diagram, it has a very minimal change in terms of characteristics or states. Let's say you have the first state, you have the second state, and the PV diagram is there, and this transition from 1 to 2 is indicated by PdV. So what you will do when you want to find out the work done, you will indicate that PdV part, and considering it with the two boundary cases 1 to 2, and that particularly gives you the work done. So work done is basically the area which is there in that particular region. So when we talk about the isobaric process is that process in which the pressure remains constant. So 1 to 2 are the states and the pressure remains constant. W12 is that particular thing. So what you will do, PdV, same condition, you will integrate it because pressure is constant, so pressure comes out, and dV integrates to V, and then you will put in the values like V2 to V1. So V2 minus V1 will be the case. The second case is for the isochoric process. So for isochoric process, what happens, this volume remains constant. So this indicates a straight line. So PdV is there. So when this volume is constant, so the derivative of this is 0. So you will get the area which is 0. So 0 area is there for the isochoric process. Then for a case in which temperature is constant, let's say it is a isothermal case. So you have this equation which is PV equals to that RT or nRT, in which this temperature is constant, so we'll get PV equals to constant. That means P1 V1 value can also be equivalent to this particular situation. So what we will do, we'll have this PdV for the work done case, we'll integrate it from 1 to 2. In place of this V, we will have this V1 over V into dV, because we can substitute or change as per the particular relationship. Then this V1 term comes outside and dV by V is log V. We'll put those boundary condition, we'll get this V2 to V1. So this is the expression in terms of in a particular case in which the temperature remains constant, which is an isothermal process. But if it is a polytropic process states like PV raised to the power n equals to constant. So PV raised to the power n equals to constant, that can be written in terms P1 V1 raised to the power n also. So work done can be equal to PdV, and we'll integrate it from 1 to 2. What we will do, we will as in the previous case we have written V raised to the power n and V1 raised to the power n here. So this can be taken as a common value, and V raised to the power minus n dV can be integrated. So after integrating and putting in the values, we will get this expression, and this expression is particularly for the polytropic processes. Then you have the condition for the non-equilibrium process. For the non-equilibrium process, this work done is not equivalent to this PdV and 1 to 2. Let us consider a case in which we have a rotating paddle and that keeps on rotating on a particular gas. So in that particular situation, that is a non-equilibrium process, and for that this work done becomes 0. So W12 equals to 0, that means power supplied by that particular motor, that would be W12, and that would not be equal to 0. So that would be for a particular case, but if we consider it for a particular situation, let's say for vacuum, like gas and vacuum condition, so that case W12 can be 0. So vacuum leads to that 0 work value, and no work will be done on the surrounding outside that particular system. So this is particularly the case in which a gas is there in the system and vacuum is there in the system. So we stop here for a short break. After coming back from the break, we will learn the concept of this work and energy with the help of certain examples.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back to S. Chand Academy after the break, and I am Anmol Bhatia. Before going to the break, we have learned certain concept of work and energy, and we have seen certain relationships of work in connection with certain processes. Now we'll correlate that particular work expressions with the first law of thermodynamics, and we will derive that mathematical expression which is associated with the first law of thermodynamics. So we have this categorization in which this first law of thermodynamics will be valid for the closed cycle. So what is a closed cycle? This closed cycle indicates that when there is a condition which is denoted by 1, let's say P1 V1, and there is another condition which is denoted by 2, which may be P2 V2, and we follow a path to achieve this second position, and again we come back to the initial position. That means it is a closed cycle. So this closed cycle has a particular concept, and this particular concept is related to the first law of thermodynamics. This first law of thermodynamics states that energy and work are mutually convertible. So energy which is there for the closed system, integral with the circle indicates that there is a closed system, and this delta W indicates the work done, and these two indicates that there is an equivalence between the two. So how can we check, how can we prove that they are equivalent? That can be proved with the help of this mathematical explanation. So you can see here we have this PV diagram, and this PV diagram indicates that we have two conditions, 1 to 2. So what we have done, we achieved movement from state 1 to state 2 by following a particular path. That path is A path. Then we returned back from 2 to 1 by following this path B. Again we can choose the path C to return back from 2 to 1. So what we are doing, we are making this as an equivalence relationship, and we are checking whether it is a path function or basically a point function. So for this, what we need to do, we can use this explanation like 1a to a2. Yeah, this 1a to a2, this indicates the limits for delta q. Then returning back 2b to b1, 2b to b1 is delta q. So energies that we have supplied is converted into the work done. So for work done conversion, the same limits goes like 1a to a2 and 2b to b1. This is delta w. Now if we follow, let's say, path C to return back, that was having the path B. Now this one is path C. So that would be 1a to a2, 1a to a2, and then 2c to c1. This 2c to c1 for delta q. Again for delta w it would be 1a to a2, 1a to a2, then 2c to c1, 2c to c1. Now you can see if we subtract both the two equations, if I subtract first and second equation, these two terms would be cancelled out. These two terms would be cancelled out as they have the same set of limits, but these two differences are still there, like 2b to b1, 2c to c1, 2b to b1, 2c to c1. So we can club both the limits together, delta q and delta w, along with the same limits that can be clubbed, like delta q minus delta w in an integral, and that limit is 2b to b1. This is also 2c to c1. What does it indicate? As these two expressions are equivalent, that indicates that whether we follow b path or whether we follow c path, the result is same. That means they are independent of the path followed. So it denotes that it is not a path function. This difference is not a path function, rather it is a point function. So in order to indicate this particular term, which is delta q minus delta w, we denote it by a term which is e, and we can use exact derivative which is d. So this one is dE. So delta q equals to dE plus delta W. This is an expression which is for the first law of thermodynamics, which is applicable to the closed cycle condition, and if it is for the non-cyclic condition, so 1 to 2 can be written as per the expression. So this is one of the important derivation as far as your examination is concerned. Then you have a particular categorization of internal energy and the stored energy. So E indicates the stored energy or the total energy, and energy is basically the property that is being illustrated from that particular derivation of the closed cycle. Here, if I talk about certain organizations like microscopic type organization of this energy or the macroscopic type organization. So in terms of macroscopic categorizations, you have these categories like potential energy and kinetic energies, and for microscopic categorization you have kinetic energy. Apart from kinetic, you have nuclear energy, vibrational energy or whatnot. So this internal energy can be equal to, now this stored energy is equivalent to internal energy plus kinetic energy, which is half mv square, plus the potential energy, and that is equivalent to internal energy, which is this one q minus w that I have indicated in my previous slides. So we have certain other processes, like we have constant pressure processes that indicates H equals to U plus PV in capitals, and in small that can be represented. If I derivate it, so this H will have dH and U will have du, but for this I can have I need to apply that chain rule, which is P dV plus V dP, and if it is a constant pressure process, so dP remains 0, so that can be removed from here. So this can be the expression that can be used. So this is one of the expression, and when you can see that this P is constant, so this can also be removed, so dH will be equal to dQ. So this is one of the case. Another case is at 0 degree Celsius enthalpy, which is this H would be 0. So for open system we have this particular formulation, and that formulation is related to the flow process. That can be throttling process, or that can be related to compressors or other aspects. Now you have this important derivation which is related to first law of thermodynamics, and that is applied to the open system. You can see that there is a channel in which energy is entering and energy is leaving, and you have taken two cross sections, P2 V2 and P1 V1, and you are supplying some energy into the system, and the work is being done. So for this you have that equivalent relationship, which is energy plus P1 V1 plus Q equals to this particular formula, which is energy 2 plus P2 V2 plus this work, which is output work, and this controlled volume rate of change of energy which is there in that particular controlled volume. So energy 1 is equivalent to this formula, which is internal energy plus that kinetic energy plus potential energy, this same internal energy plus kinetic plus potential, and the second part is also related to that stored energy which is leaving that particular system. So this is one of the key aspect, and then these two I have already explained you. Then you can substitute this E1 and E2 values in the particular formula, and when this controlled volume do not entitles the energy change, so you can substitute that particular part equals to 0. So this can be removed from there, and you will get this final relationship, which is this relationship that indicates the difference between the two values plus the work done. But if we want to consider, let's say, certain cases like this formula we have, but if we neglect the kinetic energy, we neglect the potential energy, then we are only left with this particular formula, in which you can say that work which is equal to output work, that is m h1 minus h2 or m h2 minus h1. That is particularly for the case of steam boilers or air compressors or steam turbines or pumps. Now this is one of the example, and all these formulas remains the same, and that is basically applied to the open cycle, in which the mass can enter into the system or the energy can also leave the system or enter into the system. So this is one of the application areas of the first law of thermodynamics. So you can see certain examples, like the first example is the case of IC engines, in which you can see some cases of petrol engines and diesel engines in which the mass can enter into the system, and that energy entering or leaving case is also there. So these categorizations are some of the examples of first law of thermodynamics applicable to open systems. Now there are certain limitations of this first law of thermodynamics. So first limitation of the first law of thermodynamics is that it is observed that heat flows from the system of higher temperature to the lower temperature, and never from this lower temperature region to the higher temperature region. But heat is transferred from this hot water in a container to the atmosphere, but never from the atmosphere to the hot water by itself. So from the first law of thermodynamics, both the processes like heat transfer from the hot water to the atmosphere or from the atmosphere to the hot water is possible. But this states that energy cannot get transferred from the region of lower temperature to the higher temperature. So this is one of the limitation. Heat lost and heat gain must be equal in both the processes. So according to the second law of thermodynamics, lower temperature region region of lower temperature region cannot supply heat to the other higher temperature region. So this is one of the contradiction between the two statements. So this is one of the limitation of this first law of thermodynamics. The second limitation is that it is observed in the nature that all work can be converted into heat, but all heat cannot be converted into work. But in case of, you can see in the power plants, all the heat generated from the combustion of the coal is not converted into work. You can understand this. But the portion of heat input has to be rejected in the condenser. Let us consider another example of a running car. So brakes are applied and the car is stopped. So kinetic energy of the car is converted into the frictional heat. So if the wheel of the brakes are cooled to the original temperature, so the car does not move. And in the first property, kinetic energy in the form of work was completely transformed into heat. But in the second process, heat was not converted into that kinetic energy. So according to the first law of thermodynamics, this cannot be converted, or these mutual conversions are not possible. So this is one of the another limitation of the first law of thermodynamics. So in order to have justification, or in order to have the clear summarization, one, it does not talk about the natural direction of the heat flow, and it does not talk about the heat conversion of heat into the work. So these are the limitations of the first law of thermodynamics. So in order to overcome those particular limitations, the second law came into existence. So with this, with this we come to the end of this video, in which we learnt about certain cases of work and energy and how it is applicable to the first law of thermodynamics. Thank you.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe. And do not forget to press the bell icon.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.